Hello everyone, welcome to Civil Engineering by Sunshine Academy. Today we are starting Engineering Hydrology subject. Lecture number 1, Introduction and Water Cycle. Have you ever turned on the tap and wondered exactly how the water got there? Or why some places flood while others completely dry up? Today we are talking about the science that answers those questions. It's called hydrology. Let's break that word down. It sounds complicated, but it's actually incredibly simple. Hydro means water, and logy means the study of. Put them together, and hydrology is simply the study of water, where it is, how it moves, and how we use it. But why do we need to study water? Well, it impacts almost everything we do. Hydrology helps us figure out three massive things. Irrigation. How do we get enough water to our crops so we have food to eat? Water supply. How do we make sure clean water comes out when you turn on your faucet at home? Disaster management. How do we predict and protect our towns from massive floods? And here is the biggest challenge in hydrology today. Imagine a giant scale. On one side, you have our resource, the water supply we have available on Earth. On the other side, you have the demand, the growing population of people who need that water. As you can see, the scale is tipping. Our population is growing, which means the demand for water is putting a massive strain on our limited supply. So, what is the ultimate goal of studying hydrology? It's exactly that, managing our water resource so it can actually meet the demand of the people. We have to balance the scale. This is where engineers step in to save the day. Engineers use hydrology to control the extremes. Think about it like Goldilocks. We don't want too much water that causes deadly floods, but we also don't want little water that causes devastating droughts. Engineers build dams, reservoirs, and drainage systems to keep our water supply just right. And that's hydrology in a nutshell. It is the study of water designed to balance what we have with what we need and keeping us safe from the extremes. Look at Earth's total water inventory. Imagine the Earth is a giant bank account holding about 1,386 million cubic kilometers of water. That sounds like an infinite supply, right? But here is the catch. 98% of this water is salty and found in oceans, meaning it is packed with minerals and not easily usable for daily human needs or farming. This leaves us with a tiny slice of about 2% to 3% as freshwater. But wait, we can't easily access most of that freshwater either. Around 70% of it's frozen solid in ice caps and glaciers. Another 30% is trapped deep underground as groundwater. The water we actually see on the surface in rivers, lakes, and swamps makes up less than 1% of the fresh water, and most of that it is sitting in lakes. Rivers only hold about 2% of the tiny surface fraction. The hydrologic cycle. Water never gets finished on Earth. It just keeps traveling in a loop. Let's understand this in the simplest way. Imagine you are a drop of water in the ocean. The sun heats you, and slowly you start rising into the air. This process is called evaporation. Now you go up into the sky and become part of clouds. This is called condensation. When the clouds become heavy, you fall back to earth as rain. This is precipitation. You flow through the rivers and reach the ocean again, and your journey repeats. So the water cycle is simply earth to atmosphere and atmosphere to earth. There is no beginning and no end. It is a continuous cycle. Now let's understand phase 1 of the water cycle, going up. This process is called evapotranspiration. First, evaporation. When the sun heats water in oceans, lakes, or soil, it changes from liquid to gas and rises into the air. Second, transpiration. Plants also release water vapor through their leaves. So plants are also sending water into the atmosphere. Now combine both. Evaporation plus transpiration is called evapotranspiration. In simple words, water from the ground and plants both go up into the air. That's phase 1, going up. Now let's understand phase 2 of the water cycle, coming down. This process is called precipitation. Precipitation simply means water falling from the atmosphere to the Earth's surface. It can happen in different forms. First, rain, liquid water drops. Snow, frozen ice crystals. Hail, solid ice balls. Dew, water droplets formed on the surfaces. All these are forms of precipitation. Sometimes something interesting happens. Rain or snow may evaporate before reaching the ground. This is called virga. So, in simple words, clouds release water and it comes back to earth as precipitation. That's phase 2, coming down. Now, let's understand phase 3, losses and storage. When water reaches the earth, it doesn't all flow away. Some water gets stored and some is lost. First, interception. Some water gets trapped on trees, leaves, or rooftops before reaching the ground. Next, depression storage. Water collects in small pits and low areas on the ground. Now, infiltration. Some water enters into the soil surface. You can think of infiltration as entering the door. Then comes percolation. Water moves deeper into the soil layers towards groundwater. Think of it as walking down the hall. So, in simple terms, water is either stored on the surface or it moves underground. That's phase 3, losses and storage. Now, let's understand phase 4, runoff and global balance. After water reaches the ground, it starts flowing over the surface. This flow of water towards rivers, lakes, and oceans is called a runoff. In simple words, runoff means water draining to the outlet. Now, let's understand an important global fact. Over oceans, evaporation is greater than precipitation. That means more water goes up than comes down. But over land, precipitation is greater than evaporation. That means more water comes down than goes up. So, what happens to this extra water on land? It flows back to the ocean through runoff. This balances the system. So, the water cycle always maintains a balance on Earth. In simple words, extra water from the land goes to the ocean and completes the cycle. That's phase 4, runoff and global balance. Now, the big question, why does the water cycle keep moving? There are 3 main reasons. First, thermal differences. The sun heats the earth unevenly. Some areas become hotter, some cooler. This creates pressure differences. Air moves from high pressure to low pressure and carries moisture with it. Second, the Coriolis effect. Because the earth is rotating, the movement of air and water gets deflected. So winds do not move in a straight line. They change direction. This helps in distributing moisture across the earth. Third, Earth's tilt. The earth is tilted on its axis. This causes seasons, and seasons control rainfall patterns like monsoons. So, in simple words, sun provides energy, Earth's rotation changes direction, and Earth's tilt creates seasons. Together, they keep the water cycle moving. Now, let's understand the water budget equation. Don't worry, it looks complicated, but it's very simple. It is based on one idea, the law of conservation of mass. That means water is never created or destroyed. It, it only changes form or location. Now imagine a box. Water enters the box as precipitation. Water leaves the box in different ways: runoff, evaporation, transpiration, and groundwater flow. So the idea is simple. Mass in minus mass out equals to change in storage. In equation form, P minus R plus E plus T plus G equals change in storage. Or simply, P minus losses equals change in storage. Now for exams, we use a simple assumption. Over a long time, storage changes zero. So the equation becomes precipitation minus losses equals to runoff. In simple words, whatever water comes either goes out or gets stored. That's the water budget equation. Now let's understand the catchment area. Don't get confused with the name. It is simply like a bucket. A catchment area is the area from which all the water flows to a single outlet. It is also called a watershed or a drainage basin. Now imagine rain falling on land. Water will flow downhill and collect it in a river. All the water that reaches one common outlet belongs to the same catchment area. But how do we separate two catchments? By a ridge line, also called a divide. This is the highest line of land. Water falling on one side flows to river A, water falling on the other side flows to river B. So they belong to different catchments. In simple words, catchment area means the land area that collects and drains water to one outlet. Think of it like a bucket collecting water from all sides. Now let's understand catchment leakage. Normally, surface water and groundwater follow the same route, called the divide. But sometimes they don't match. This is called catchment leakage. On the surface, water may flow towards catchment A, but underground, water can move in a different direction. So groundwater may actually flow into catchment B. This happens because surface shape and underground geology are different. In simple words, surface water goes one way, but groundwater leaks into another basin. That is catchment leakage. Now let's understand the residence time. Don't worry about the formula, it's very simple. Residence time means how long water stays in a system. The formula is residence time equals volume divided by flow rate. In simple words, if water volume is large and the flow is slow, it stays for a long time. If volume is small and the flow is fast, it stays for a short time. Now look at the ocean. It has a huge volume, but water moves very slowly. So water stays there for thousands of years. Now look at a river. It has less water and flows very fast. So water stays only for days or weeks. So remember this simple idea. More water and slow movement means longer stay. Less water and fast movement means shorter stay. That's residence time. Now let's understand the runoff coefficient. Don't worry about the formula, it's very easy. Runoff coefficient means what percentage of rainfall becomes runoff. The formula is runoff coefficient equals runoff divided by rainfall. In simple words, out of total rain, how much water actually flows on the surface. Now think about a city. In urban areas, we have concrete roads and buildings. Water cannot go inside the ground easily. So most of the rain becomes runoff. That's why the runoff coefficient is high. It is around 0.7 to 0.9. Now think about a forest. In rural areas, soil and plants absorb water. So less water flows on the surface. That's why the runoff coefficient is low. That is 0.3 to 0.5. So remember this simple idea. Hard surfaces gives more runoff. Soft soil gives less runoff. And this value is very important. Engineers use it to design drains, roads and dams. That's the runoff coefficient. Thank you for watching. If you like the video, please like, comment, subscribe and share. Thank you. Have a nice day.